All right, let's look at another couple calculations for free energy, and then let's consider equilibrium and off of 1 atm or 1 molar, and see if we can do off of standard state as well. So we know that we can take delta G of a reaction, and we can calculate it from the delta G Notzer formation of the products and the reactants. And if we are working at 298 Kelvin or 25 degrees Celsius, we use this because it's by far the simplest. But if we are not at 25 degrees Celsius and we need some other temperature, we are going to use this version right here. So again, we have two. We have off of the charts at 25 degrees Celsius, and we have to, if we're off at 25 degrees Celsius or we're looking for the temperature, then what we're going to have to do is get delta H, delta S, and find ourselves a T and get delta G that way. So not at 25 degrees Celsius or 298 Kelvin. All right, let's consider bromine as a liquid going into bromine as a gas. The temperature at which this occurs spontaneously, where delta G becomes negative, the temperature at which that occurs is the boiling point. Now, we have no reason to believe that this is at 298 Kelvin, so we're going to have to use the equation of delta G is equal to delta H minus T delta S. Now, to do this, we have to be given some information. So we are given a delta H and a delta S for this process, the change in heat and the change in entropy. Now, note these are both positive. Because these terms here are both positive, we know that this reaction is going to be spontaneous at high temperatures. Let's think about it for a moment. In order for this reaction to be spontaneous, delta G itself has to be negative. Delta G is only going to be negative when this T is large enough. If the T is too small, then our delta H will sort of swamp the whole thing, and this delta G will be positive, and the bromine will not boil. So what are we going to do? We're going to set delta G equal to 0 and solve for T. Why? Because if the temperature is large enough, delta G is negative. If delta G is positive, that means the T is too low. And delta G equals to 0 is the transition between not spontaneous and spontaneous, meaning that we're going to actually be finding the boiling point. Well, if this is the case, if we have delta G is equal to delta H minus T delta S, and we want to solve for a T, we are going to set delta G equal to 0, because that is the transition point from spontaneous to not spontaneous, or vice versa. So let's do the math. If we have 0 is equal to delta H minus T delta S, and we rearrange this, we're going to get delta H is equal to T delta S, or delta H over delta S is equal to T. Now we have to watch our units. We were given that delta H was 31 kilojoules per mole. Here we need this in moles because, or excuse me, in joules, because delta S is given here as 93 joules per mole K. Because S and H have different units, we're going to fix them, and we're going to say here that 31 kilojoules multiplied by 1,000 joules per kilojoule for delta H divided by 93 joules per mole K. I better put the moles down here as well. Our joules cancels, our moles cancel, and all we are left with here is a unit of Kelvin, and we get 333 Kelvin. This tells us that if the temperature is greater than or equal to 333 Kelvin, this reaction is spontaneous. So let's do another one. We want Gibbs free energy, maximum available amount of work, for this reaction at 400 Kelvin. So we're given T. So we are given the T value. We know it's not 25. So if we're given the T and we know it's not 25, our equation is going to be delta G is equal to delta H minus T delta S. And we have to get delta H off the charts. We have to get delta S off the charts, plug in the value of T, and see if we can get delta G. We cannot get delta G straight off the charts because It is not at 25 degrees Celsius. So we need some values. We know that to solve for delta H is the sum times the moles of the products minus the sum times the moles of the enthalpies of formation of the reactants. We need to look these up. So when we look these up, we're going to find delta H not a formation. And if we tabulate these, and we have SO2, O2, and SO3, SO2 is minus 297 kilojoules per mole. Oxygen here is going to be 0, and SO3 is minus 96 kilojoules per mole. We know it's products minus reactants, so we're going to have delta H naught for this reaction is going to be 2 moles of SO3 times minus 396 kilojoules per mole minus, again, products minus reactants, 2 moles of SO2 multiplied here by our value minus 297 kilojoules per mole plus 1 mole of oxygen multiplied by 0. When we finish our math here, we're going to get a delta H naught for this reaction equal to minus 198 kilojoules. Please note the moles are going to cancel. So do the same thing with delta S. Same thing with delta S. We're going to need the values of S for SO3, SO2, and O. For SO3, our entropy here is 257 joules per mole K, and that's our S value. For SO2, it is equal to 248 joules per mole K. And for oxygen, and by the way, the elements are not zero with entropies. Everything has some disorder unless it's at absolute zero. So those are our entropies. So we're going to start out with products minus reactants. So we're going to take 2 moles of SO3 multiplied by 257 joules per mole K minus 2 moles of SO2 times 248 joules per mole K plus 1 mole of oxygen times 205 joules per mole K. And when we finish our math here, we're going to get a delta S for this reaction equal to minus 187 joules per Kelvin. The moles are going to cancel. Note our delta S here is negative, which makes sense since this is coming together and becoming more ordered. So we need to put it together. So let's put it together. Delta G is equal to delta H minus T delta S. Delta H is minus 198 kilojoules. Temperature is given as 400. You can put any temperature you needed to in here. The delta S is minus 187 joules per Kelvin. We have to get these units to work. So in this case, I'm going to put it in kilojoules for no particularly good reason. If I do this as 1,000 joules per kilojoule, and when we combine these, it is not as spontaneous as it was when it was colder, but it is still spontaneous at minus 123 kilojoules. All right, can we sort of put all of this together? Well, we can actually put this together and we can do equilibrium. So we need one more equation here. And our final equation here is that delta G is equal to delta G naught plus RT times the natural log of Q. And here, this tells us that our Gibbs free energy, note the little zero here means standard state. So our delta G is equal to delta G naught, standard state, plus RT times the natural log of Q. Well, in case you forgot Q is the reaction quotient, which is going to equal the products raised to their stoichiometric coefficients over their reactants. And what we can do is find out how much work we can get for a system off of standard state. Now, remember here that if Q equals K, we are at equilibrium. When Q equals K, delta G itself is equal to 0. We have no work available when we are at equilibrium. It's sitting there, it's in a stable form, and our delta G naught is equal to minus RT times the natural log of K, which means that if we've got a delta G, we can actually calculate equilibrium constants. So what does this mean? Well, let's just imagine that we have, in a sense, a ball rolling downhill. If we've got this rolling downhill, it is going to become, or will be, spontaneous. If it's going here and it's going uphill, it is going to become not spontaneous. If it's sitting here at the lowest point, then we are having no change whatsoever, and we can take and we can relate our delta G to where we are in terms of our reactants and our products. So delta G equals 0, we're going to be at equilibrium right here, and we can see how far off we are using our reaction quotient. So given that delta G is equal to delta G naught plus RT times the natural log of Q, at equilibrium, delta G is equal to 0, Q is equal to the equilibrium constant K, and delta G naught is equal to minus RT times the natural log of K. Now we do have one issue with this, and that is when we're finished calculating delta G naught, we lose the units of moles. Remember that delta G naught here is the summation times the number of moles times the delta G naught of formation. And when we do this, our moles term is gone. Well, the problem with that is R here, because this is in energy, is 8.314 joules per mole Kelvin. Over here, there's no moles, so we're just going to do something appallingly sloppy. We're going to remove the mole term here, and we're just going to ignore it. If we are at 298 Kelvin, so if we're at 298, we would plug 298 Kelvin in here, and we get our delta G off the charts. If we're off of 298, we'd use whatever the other temperature is, and we would get delta G, delta H minus T, delta S. So let's do a calculation. All right, so if delta G here is 0, our K is going to be 1. Nothing's going to be happening. If delta G is negative, this means the reaction is spontaneous. And our K is going to be greater than 1. Delta G is positive here, greater than 0. It's going to be non-spontaneous. And our K here will be less than 1. So we can calculate our Ks. So let's imagine that we have silver chloride dissolving into silver and chloride, which, by the way, is going to be KSP for this. So let's do this reaction at 25 degrees Celsius. If we do this at 25 degrees Celsius, we can get delta G naught from this reaction from the charts. If we plug in a temperature of 298 Kelvin, we can get the equilibrium constant. So let's get the delta G naught for this reaction as well as the K. By the way, we've seen this before. This is just a solubility product. If we're looking for this reaction, we need the delta G naughts of formation. If we look these up, delta G naught of formation of silver plus is 77.1. Delta G naught of formation of chloride is equal to minus 131.2. And delta G naught of formation of silver chloride is equal to minus 109.8. We're going to do products minus reactants. So delta G naught of this reaction is going to be 1 mole of silver times 77.1 kilojoules per mole plus 1 mole of chloride minus multiplied by a minus 131.2 kilojoules per mole minus 1 mole of silver chloride times a minus 109.8 kilojoules per mole. And when we put this together, we're going to get a delta G naught of this reaction equal to a value of positive 55.7 kilojoules. Now, we can use this to calculate K. If delta G naught for this reaction is equal to a value of positive 55.7 kilojoules. We know that delta G naught for this reaction is equal to minus RT times the natural log of K. We're given that the temperature on this was 298 Kelvin. So if we look at our units and we plug this in, because the units of R are in joules, I'm going to take my kilojoules here, multiply by 1,000 joules per kilojoule is equal to minus 8.314 joules per mole Kelvin, ignoring the mole, times 298 Kelvin, multiplied by the natural log of the equilibrium constant. When I finish rearranging this, I'm going to get the natural log of the equilibrium constant is equal to minus 22.5. My units cancel, and K is equal to 1.7 times 10 to the minus 10. By the way, we calculate things like KSPs from things like delta G naughts because we can tabulate these values, and sometimes these equilibrium constants are pretty hard to measure. All right, so let's consider a reaction off of standard state. We know that off of standard state, and we know we're off of standard state because our values here are not all at 1 atm. Remember standard state here, if we wanted delta G naught, this would mean that everything would have to be at 1 atm. These guys are different from that. To do this, our equation is delta G is equal to delta G naught plus RT times the natural log of the reaction quotient Q. Well, delta G is going to be products minus reactants. So delta G for this on standard state will equal 2 moles of ammonia multiplied by minus 16.5 kilojoules per mole minus 0 plus 0 because both delta H naughts, the formation of hydrogen and nitrogen, are 0 because they're elements. And this is going to give us a value of minus 33 kilojoules. Now, that's delta G. What about Q? Q is going to equal pressure of ammonia squared over the pressure of nitrogen times the pressure of hydrogen cubed, which is going to equal 1 over 33 multiplied by 99 cubed. That one would be squared. This would equal 3.1 times 10 to the minus 8. So if we plug all of this in, we're going to get that the change in Gibbs free energy for this reaction off of standard state is going to equal minus 33 kilojoules. There's 1,000 joules per kilojoule plus 8.314 joules per mole K, again ignoring the mole, multiplied by 298 Kelvin times the natural log of the Q value, our reaction quotient of 3.1 times 10 to the minus 8. When we plug all of this in, we are going to get that our delta G for this is going to be a value of minus 76,000 joules. So let's put this together. Our original value for delta G naught at standard state was minus 33. We know we started with nitrogen plus 3 hydrogens goes into 2 ammonias. Now this reaction is spontaneous, but we looked here at our pressures. If we had 1 atm of this, 33 atms of this, and 99 atm of hydrogen, we're noticing that the pressure of the reactants went up. Well, according to Le Chatelier's principle, if we increase the amount of reactants, our reaction shifts towards products. Well, we went from minus 33 kilojoules to minus 76 kilojoules, and our reaction became significantly more spontaneous because the pressures went up, which is consistent with Le Chatelier's principle.